Welcome to a lesson with Dr. Powell. In this video, we are going to look at an application problem using derivative information to find the minimum of a function. Now, the minimum of what? We want to find the minimum distance between this point, -3, 4, and this curve, this parabola. So the closest distance from this point to a point on this curve. Now, whatever we're trying to minimize is going to represent the output of the function that we need to write down and take derivatives of and so forth. So what is that function? The function is going to represent, we're trying to minimize distance, so the function should represent distance, okay? So distance between a point on the parabola and this point. Now, a point on the parabola depends on something. So these functions, we want them to depend, at least in these videos right here, on one variable. So what are the points on the curve depend on where we plot them? Well, it depends on x. It's a function, right? So it depends on the input. The output depends on it. So the input, if the input's x, the output is, well, it's given to us right here, x squared plus 6x plus 9. Now, we want to find the distance between this point and this point. So to find the distance between 2 points, think that there is kind of a right triangle lurking. And we're interested to know what the length of the hypotenuse is. Well, to know that, you simply need to know what this length is and what that length is. What are these lengths? This is like the difference of the y values, with the change of y, and this is like the difference of the x values. So you can line these 2 points up, -3, 4, and then simply subtract to get those two lengths. So so that's like an x plus 3. This is like your change of x length, right? And then right here you subtract, so you're going to get x squared plus 6x plus 5, and that's going to be like your change of y. Okay, so all we need to do is take this length, square it, and add it to this length squared. So we get x plus 3 squared, Pythagorean theorem it, plus 6x plus 5, quantity squared. And then, of course, to find the hypotenuse, you would take a square root. Now, the nice thing is that if you make the inside as small as you can, of a square root, doesn't that also make the x value that would make the inside the smallest it can? Wouldn't that x value also make what comes out of the square root the smallest it could be? It's like this. The square root function looks something is increasing. And let's suppose we have kind of some things that happen before you square root. If we were to take the minimum of what happens before we square root, like what's on the input when the x values of the square rooting process, so if you take this part of an interval, like the minimum that's going into it on that interval, if we look at what happens with the output interval, that also, this corresponds to the minimum output, minimum input, minimum output. That idea tells us that the x value that minimizes what goes before the square root is the same x value that will minimize what happens after we square it. It'll minimize the distance. So to find that x value, for simplicity, let's ignore the square root, because we'll be needing to take a derivative anyhow. So let's let this be our function, and the x value that will minimize it will also be the x value that will minimize the actual distance, which is the square root of this. So let's begin by taking a derivative before we even multiply this out, because we have like power rule and chain rule and stuff, and that's actually pretty handy in this case. So here, let's see, if we take L prime of x, this would be simply, think power rule, the derivative of the inside is just 1, so that's nice. So just 2x plus 3 times the derivative of the inside, which is just 1, so that's good. And over here we have, again, power rule, 2 times x squared plus 6x plus 5 times the derivative of the inside. The derivative of the inside is 2x plus 6. Now, that's convenient here in this case, because if you can factor out a 2 out of that, so a 2 out of this part right here, we could think of this as being 2 times x plus 3, right? Ooh, yeah, and then kind of times going up, so we can kind of erase that and think of this times this going up there. X plus 3 is a common factor, so we can factor it out. So we get x plus 3, and then notice we have a, okay, so x plus 3 is, in fact, even 2 times x plus 3 is a common factor. Oh, that's kind of nice. So that whole thing, 2 times x plus 3 is common. So that means you're left with a 1 from that, and then here, that's gone. So it's just like, just 2 times all of that. So plus 2x squared plus 12x plus 10. All right, so that's our derivative. All right, and our derivative is, look, it's already in factored form almost, which is kind of handy because we want to know where this derivative is equal to 0 to look at critical points. And it's always defined, so it's just places where it's 0. So we need to figure out where this part will be equal to 0. So we can rewrite this as 2x squared plus 12x plus 11. Okay, now we're going to use a little trick that I have in another video about quadratic formula completing the square. So if we make a little synthetic division diagram, so if you want to follow this, you need to look that up. So right here, okay, so I make a little synthetic division diagram, and what I do is simply you drop that 2 here, so you don't have what goes there, but we can get it simply by just taking half of this 12, 6, and then take, say, this, divided by that, change the sign, so -3. Then you take this, -3 times the 6, which is -18, and then we add, going down, which would give us -7. Okay, so pretty much we have everything we basically need. So 6 divided by this change of sign is that. It's -3. So really we're going to have -3 plus or minus. So this is kind of the beginning of what x is equal to when we set it equal to 0. So x is equal to -3 plus or minus, and then square rooting. What's in the square root? Square root is actually this guy. So remember how we took this divided by that, change the sign. Now take this guy divided by the first guy and change the sign. So 7/2. Okay, so it's -7 divided by 2, but then change the sign to positive 7/2 and taking a square root. So it looks like, so it's a real number, so it's going to be a critical point for us. So, okay, so we have something to work with. -3 plus or minus the square root of quantity 7/2. So we have some critical points for the derivative because we know where this guy is going to be equal to 0 here, and we know where this factor is equal to 0. It's equal to 0 at x equals -3. Okay, now if we were to look at my strategy for quick sketching, analyzing these critical points, here I have some videos on this using sign determining polynomials. You can look at that. The end behavior of this whole polynomial is you look at the leading terms of each factor, x, and then this guy, multiply them together. It's going to look like 4x cubed, which looks like this is a graph going up. So you're going to start down, up. Where does it hit the axis? It hits it at, let's see it, there's a -3, and, well, the first one is actually at -3 minus, let me just rewrite that. negative 3 minus square root of 7 halves. And then the next place will be at negative 3, and then after that, negative 3 plus square root of 7 halves. And and then as it hits, so it's going to start down, going to end up, and as it hits each point goes through with multiplicity 1, since this has multiplicity 1 here, and really there's only one of these. These aren't double roots at all, because you can use this number to actually these two numbers to factor this quadratic, like x minus something times x minus something, or something like that. So really these have multiplicity 1. So you're just going to shoot through each time. So it's going to come up, shoot through, come down, shoot through, come up, shoot through. This is like a graph of the derivative, kind of a rough sketch of it. And looking at that, so you think, okay, what's happening with the actual function? Right here, this is negative derivative, so that means you're going downhill. Then positive derivative means you're going uphill. Then negative derivative means you're going downhill. Then positive derivative means you're going uphill. Notice we have a max here, and we have a minimum here and a minimum here. Actually, the two x values that correspond to these points right here actually give you the minimum distance. So in order to find the minimum distance, what would we do? We'd have to plug in one or both of these and check to see, if one's less than the other, or maybe they're both the same. Plug them into the actual, well, this is the square of the distance, right? So if you were to plug these into the square of the distance and then just square root that, you would get the actual minimum distance length. But at least we found the x values that correspond to that. Notice that there is a critical point that actually represents a maximum, not a minimum, so you'd have to be careful. Now, also keep in mind that this maximum is only a local maximum, because in reality this curve has points that get way far away from this one. It's impossible to have an absolute maximum here, or a global maximum in this case, but maybe locally nearby it should make sense here. For instance, if you had like a parabola and maybe you had a let's see here, kind of thinking of a situation here. Perhaps it's closer here and here, but further away straight down, depending on how the parabola sits. So maybe this is like a local maximum, but then maybe you have a minimum here and a minimum here, and those would be your minimum distances. So there's different ways of thinking about that, but in this particular case, that's what you would get. And that concludes so we'll forego the actual plugging in to find the distance, but the interested viewer can do so on their own. Thanks for watching.